All right, hello everybody. So, got some unfortunate news. My big fancy Themis microscope is injured at the moment and can't use it. We got a problem with the gun, and things currently inoperable right now. But I've had a idea for a video that I've been wanting to do for quite a while, and that is talking about an aspect of STEM that I don't think gets the attention that it probably should, and that is talking about beam-induced damage to your specimens. Okay, so I'm just gonna, while we're working here, I already have a sample loaded in here, which we will talk about here as we're working. But one thing you should appreciate is that at the voltages that we perform STEM, okay, so tens of kV, through hundreds of kV, you are going to cause damage to your samples. Okay, so there's lots of different kinds of beam-induced damage that can occur to your samples. When we talk about the physical sciences, we're mainly concerned, and again, not to say this is the only type, but mainly we're concerned with what's called knock-on damage. Okay, so knock-on damage is where electron comes in and it physically knocks an atom off of its equilibrium lattice position. Okay, so essentially, right, it causes a point defect. Okay, and we call this knock-on damage. The amount of energy required to create knock-on damage is not high. We're talking about the order of a few eV to maybe 10 to 20 electron volts. Okay, and remember, your electrons are going through 200 keV of energy, or even if it's 80 keV of energy. Okay, so just looking at the energy balance there, you have more than enough energy to cause knock-on damage. Okay, and so you most certainly are doing this when you are imaging your sample. Okay, um, but you may never see the effect of it, right? Because as you create the damage, right, as you create point defects, there's obviously some recombination of the defects. So you have damage generation and you also have damage removal at the same time, right? Because you're creating like an activated state with the point defects. And so some of them recombine. And so um, obviously it's, seeing point defects, not to say that we can't do it in STEM, but usually we don't directly see the point defects. But if we get enough of the point defects, what we can see is our extended defects. Okay, so we get enough point defects, we can see things like stacking faults, dislocations. We may even eventually be able to see things like amorphization, right? Because if we start with a perfect single crystal and we create enough point defects, we can end up with something that is actually not crystalline anymore or just amorphous. We could even burn a hole straight through the sample, right, as well. Okay, that's something that we're not going to use STEM mode today, but you could do this while you're talking about STEM as well. So so that's what we're going to discuss today. And so the sample I have in here is as close to a perfect sample as I have. So this is it's a silicon sample oriented. So we're going to be looking along the most studied zone axis ever, 110. And it is prepared, I think, exclusively by precision mechanical polishing. So it should have basically no damage layer from any sort of ion beam process, right? Whether that's fib, whether that's ion milling, anything like that. So basically only like an oxidation layer. So this gives us really the perfect starting structure, if you will, to kind of see how we can generate beam-induced damage, okay? So right now, as you can see here on my flu cam, I've got the whole beam here. I have around 1.3 nanoamps of current in my beam. Okay, so what we're going to do is we're going to go find a place to take some images, and we're going to play around with this current, and we're going to watch how we can alter the appearance, right, with, you know, with changing this dose. Okay, so let me pull back over here to the left. Okay, so you can see this is the edge of the sample right here. I've got vacuum on the left, and then this is my silicon here. So now I think I'm gonna have to go back into diffraction here to see, but I know I've got, and you can see there's some burn marks already there. Interesting. So let me see right here. Want to be close to the zone axis. Okay, so that's really close right there. Now if I drag back over, okay, so really, and we get a little bit off the zone. So really about in here, it's not too bad. We're getting quite a bit of Kikuchi diffraction, but for what we need to do, that's okay. We can still see what we need to see here. See if we can't get this a little bit better. Okay, right about there is pretty close to perfect. I'm going to go ahead here and put in my objective aperture. I already did a lot of the alignments, by the way. I already did pivot points and rotation center, so I just need to put the aperture in. Centering looks good. So we'll go back into image mode. Okay, so I can remember this. I have the spot right here. Let me go back over here, though, to the edge, because I'm going to use this to help us tune up the picture. Okay, I'm going to go all the way to, we can stay at 500K. That's good. All right, let me focus a little bit better with the Z, just like there. And now I'm going to head to Velox. FFT. Okay, so my defocus right now is 0, so I'm going to go up here because I can see I'm still a little too under focused. So right about there. Oops, let me go back up again. Okay, that's close enough right there. All right, so we can see in the FFT, I've got some major twofold astigmatism here. So I'm going to come back here to Tune tab, find Stigmator Objective. Whoops. And it'll get us to a nice circle. Okay. Okay, now let me check here. Okay, looks good. All right, and again, right? So you can see my defocus here is pretty small. I want a slight underfocus. Now when I move over to my spot of interest, I may have to change this, but we'll leave this here for now. So, okay, so you can see I can't really see, I mean, the lattice detail isn't good here. I'm near the edge of the sample where I've got a lot of oxidation. You can start to see some lattice in here, but let me put the screen back down. Plus we kind of remembered where we were looking here. I'm going to drag over. And where's my bullet hole? Did I really lose it that much? Where are you? I guess I did. I can't find the spot. Let me see here. Natural, no. Well, I guess since I can't see those holes anymore, I guess we'll just have to. All right, let me go back here. We've got a clean looking area here, so all right, we'll leave it right here. All right, so let me go back up to 100 or 500K. All right. All right, so we can see the lattice here pretty clean. Now focusing here is going to be a little bit of an adventure because we don't have any amorphous signal here to look at, okay? So since we kind of focused at the edge, we can just kind of assume that it's still good here. I mean, it looks reasonable. So let me go ahead and do an acquire. Okay, and there we have really nice high-res image of the silicon. See if I can't tweak with the focus a little bit here, but yeah, it's hard to tell. Again, when you don't, this is such a nicely prepared sample. You can't really get any rings in the FFT. So these are tricky when you come across them, right? But this is kind of nice too because you have a really good sample. All right, let me put this down. Let me go up one more mag click. Okay, looks good. Wonderful. Okay, so we can see all this detail here, really no damage layer. Obviously, nothing that looks like a stacking fault or a dislocation, right? Okay, let me try it again here. Oops. Okay, great. Okay, so you can see right here. Oops. No, I don't want that. 0.1 nanometers. There we go. Okay, so we're actually getting detail here. As you can see the spots here, right? So that's actually beyond 100 picometers in terms of the detail, which is, great in terms of the information limit here. Let me see, yes, I can scroll in here. One thing you can do too, you can play around just by looking at the appearance of the lattice, but this can be kind of tricky because you get lots of contrast reversals when you do this, so you can end up looking exactly the same for a bunch of different defocus values, which is one of the reasons why this becomes tricky to interpret. But anyways, we're not talking about interpretation, we're talking about damage. Let me take one more picture here. Okay, so we lost some of those higher order spots. So I'm guessing, yeah, so I'm guessing that means the focus needs to go back out here. Let's see what that. Yeah, so we're seeing those higher order spots better now. Okay, so what you'll notice here, right, though, is my silicon lattice still looks pristine, okay? I'm not seeing any sort of damage here, okay? So, and again, I've got about a nanoamp and a 1.3 nanoamps of current, I should say, okay? So what we're going to do here is we're going to play around with this And well, I guess I could have marked the stage position here, but at this level, I don't think it would have come back anyway. What I can do here, though, is I'm going to increase my beam current by changing spot size, and we're going to see what happens as we do this, okay? I'm moving over to the edge here so we can be in vacuum so we can see the full effect. Yeah, so the edge focus looks okay. Again, as you move in, right, you don't have the sample, you know, there's variation in the height and whatnot. So, all right. So right now at spot 4 with this C2 aperture, we're getting this much current. If I go to spot 2, I should get about 4 times the current. Okay. So not quite 4 times the current. Let me go to spot 1 here. Again, I would never do this in practice. I'm just doing this for, okay, so we got about 4 times the current because now we're getting about 4 nanoamps, okay? Technically speaking, you change the spot number, you know, your rotation center, your pivot points, that should be still okay, but, you know, let me go ahead. I mean, the C2 aperture is probably going to need to be tweaked again, so I can check it here. All right, so yeah, so you can see that is off. Okay, that looks pretty good. All right, see some asymmetry in the beam, so let me go ahead and correct that. So we have a circular incident beam here. All right. Okay, my pivot points are a little bit off here. All right, and then let me mag up higher here so I can use the edge here. The rotation center should still, yeah, the rotation center is fine. Okay, so you can see, right, I've got a lot more signal in my image, okay, because I increased my my current. My objective stig should still be fine. I can go ahead and check it anyway just to show you that. Yeah, see, this is still fine. Now you can see the focus here. I can set the defocus back to 0. So we're getting a little bit of settling here, probably with the sample. Okay, let me see if I can focus with the Z. Okay, that's pretty close right there. Okay, there's a little bit of astigmatism still now, I think. That again is going to vary with time. It doesn't stay good forever once you correct it, so. Okay, so that looks pretty good right there. Okay, so the focus is pretty good here. So now if we drag over, we can use that as our starting point here. So let me mag out here. We'll drag over into the middle here. We're not going to be able to find the exact same place, but we don't need to for what we need to demonstrate. Okay, it's getting a little thick in there. This should work fine. All right, so let me increase the mag up to, and yeah, we took some at 630. Let me go to 630, okay? So now I am pumping way more electrons into the sample than I was, okay, previously. All right, so I'm getting way more signal. but I'm also causing damage way quicker, okay? So now the question is, okay, good looking image. Now the question is, how long is it going to take for us before we see this? Okay, so the beam spread out a little beyond the edges here, so we're not seeing the whole beam, okay? But I don't think it's going to take very long. In fact, I'm starting to see it already right here. Okay, so I'm just going to take images here periodically. Four nanoamps in general is pretty high for doing high res work when you're putting current into that small of an area, at least in my opinion. Okay, so far so good here. All right, so this was before when we had spot number 4. Still a decent picture, right? Okay, let's see though. Let me put this screen back in. Okay, so we're not seeing, so we're starting to see the beam-induced damage a little bit here. Maybe what we can do, so I can start to see some of it right there, actually. Yeah, so you can start to see this coming in now. Okay, so it starts with some of this. So it shouldn't take us too long here before we actually start to see some of these extended defects, which I was referring to. And again, obviously, the smaller you make the beam, right, the higher you make the current density, the faster this is going to happen. Okay, we're still getting there. But that'd be pretty funny if it wouldn't damage on me, I suppose. I know that it will though. I've seen it do this before. So All right, well, maybe we need to kind of speed this up a little bit. Now I'm curious, if I move over here, do we see like a demarcation line? Yeah, so we kind of do. All right, let me go ahead, put the screen in. I'm not going to do this on the camera, obviously. I'm going to do this on my blue screen here, but okay, so I'm a lot closer to crossover. Again, I would never do this on the camera itself, so I'm just going to do it here, but we're just going to accelerate this a little bit here, right? So now we can start to kind of see what's going on here. And once we've kind of cooked things a little, I'll spread the beam back out and we'll take a look at our handiwork here. Okay, let me spread it back out. Still not really seeing any extended defects. I mean, there's a little bit of, let me take the picture here. There's a little bit of this kind of low frequency modeling that we don't see. Like this was the lower dose image, right? We don't really see any of that. So that again, yeah, so here's where we are now. Here's where we were initially. Here's where we were initially. All right, let me see here. No, still not seeing anything. All right, let me put the screen back in again. Okay, I think we're starting now. All right, let me go back here. Of course, I've said that a few times, so I'd understand if you didn't believe me. Ah, okay, so now we're starting to see, yeah, this stuff here, okay? So we're seeing the beginnings. Let me take a picture. All right, let's take a look again. Okay, so now it's, I think, pretty obvious. Yeah, so now we're seeing the beginnings of some extended defects here. Okay, let me put this down. Continue cooking the sample here. So let's go back here. Okay, so this was the first image we took with the 4 nanoamp beam, right? And we'll just keep going. Okay, starting to see. There we go. Okay, so I mean, you can see what's happening here, right? As I'm continuing to dose the sample here, okay, is that I'm imparting damage, right, faster than it can apparently be removed, okay? And so I end up modifying my material here. All right, let me take a look again. Yep, and there we go. So we can really see the effect there. This was actually more robust than I thought it would be. I thought it would take not as much time, and not with the beam being that close to or that converged to see it. But I mean, you can see it, right? Start to finish. Okay. Now again, this was with the lower dose here. Okay, before we did anything, and we've taken a bunch of these images here. Wait, no, sorry. This is the high dose image. This is the lower dose image. Okay, right here. So again, right, we're taking a hit here in terms of the signal to noise, okay? But the advantage of that is we're not having to worry so much about cooking the sample here, okay? That's always the trade-off, right? Everything has a trade-off, okay? So if you want to go, high with the current, right? So again, right now I've got about 4 nanoamps versus when I took this image, it was about 1.3 nanoamps, okay? That's what you're going to have to, keep in mind. So you have to be just kind of cognizant of this as you're working, right? And you have to look and see, okay, what's happening to my material, right? And I'm modifying it by what I'm doing right now. And chances are with time, you probably will be doing that, okay? I mean, we can see very clearly now we've created a nice gash here on the sample, if you will. Let me put the screen back in here. Yeah, so it's pretty obvious even on the flu cam here. Okay, let me take one more picture of this. Just so we have it. Okay. Now again, you can see the trade-off here though, okay? I'm getting all the way up to 3,000 counts. Again, the range on this camera I think goes to 8,000 counts in the for the same exposure time, okay? Versus, where is it? Okay, so versus, no, not this one. Okay, so versus this one, I'm only getting about 1400. Again, the beam might not be spread out exactly the same in both cases, so, but that is the trade-off in terms of signal to noise. But again, even at this lower this lower dose, right, and this lower current dose rate here, I'm still getting, what's very much a workable image here and a good image, okay? So the just kind of the takeaway I have from this for you, right, is try not to cook your samples, okay? You don't need as much current as you probably think you do, okay? If you have a decently prepared sample, I guess so the question then is, well, where do you start? I like to start, somewhere between 1 to 1.5 nanoamps, just for general bright field / high resolution, aka lattice imaging. That's usually where I like to kind of start with things. I think FEI, they usually recommend spot 3 as a default, and again, that depends also on how you have the gun set. But again, back when we set this up, right, and again, I have an objective aperture in here. We're not over vacuum, so this is not the actual current. That was closer to 4 nanoamps. But when we went down here, right, and we put this at spot 4, we were getting about 1.3. So actually, let me just drag back over. I mean, you can see now, right, this is where we haven't been cooking the sample, so I don't see the same stuff, the same accumulation of damage. Yeah, so you can see here, I've got basically 4 nanoamps. If I go back to spot 4, okay, yeah, I got about 1.3, okay, 1.2, 1.3. So again, a little bit of a drop off, but again, in my opinion, that's worth it, right? In order to get a decent image. Of course, you can make this too low, okay? So you always have to balance the trade-offs here, right? So if I want to go to say spot size 6 or 7, right? Let me go to spot 7 and see how much current I get here. Okay, so I'm only getting about 200 picoamps, okay? Let me go ahead and quickly realign this, okay? Because the C2 aperture is going to depend on the spot number on this machine. Okay, that looks decent. Okay, my condenser astigmatism also looks decent. Okay, let's check our pivot points here. All right, so that's off a little bit. Okay. And then my rotation center should still be okay. Now the FluCam is going to have a harder time with this though, because we've got less current, right? But you can see it's still going straight in and out. We're still pretty good here, okay? All right, so let me mag out here. It should be easy now to find that area that we just spent. There it is, right? There's ground zero, right, where we've been cooking the sample. Okay, so presumably up or down from this, we should still have some decent zone axis alignment, and we haven't been cooking the sample as badly there. So we will go back up to 630K and take a look. All right, so you can see this is pretty terrible. Okay, we're only getting about 40, yeah, 40 counts here, okay? The FFT, we can actually see some of the spots, right? So the FFT math is still telling us you've got lattice detail in here, but it's going to be very difficult here to use this. Now we could try, right, using a long exposure here. The problem with that, of course, is it makes your sample susceptible to instability from drift, okay? But let me take a 1 second exposure like we've been doing. Okay, so we can actually see, we can still see a lot of the detail here, but you can tell very quickly it's a very noisy image, okay? It's a very noisy image here, okay? And that's bared out by the histogram where I'm not even getting to 200 counts maximum, okay? So now in principle, if I multiply the exposure time by 10, I should up this by 10, okay? And that should give me a comparable image to what I was maybe getting at spot size 4. The question then though is, okay, if you're going to do that, you might as well just use spot size 4 and take it for 1 second, right? Because ultimately your dose is the same, okay? You only want to do this if you gain something, right? But you can see, right, the cost here in terms of the signal to noise is just pretty staggering, okay? We can try doing one just for the sake of argument. We can try a 10-second exposure and see. Okay, so yeah, decent signal. Not too bad. I mean, there's definitely some drift there. Becomes very hard to focus, right? I mean, even if we had, you know, some amorphous area in here, it becomes very hard to do that though, just because of the signal to noise, okay? So everything's a trade-off, right? We're not really hurting the sample right now, at least not quickly enough to really have it be an issue, but, you know, again, the trade-off in terms of the signal to noise is just too much. If we had a better camera, we might be able to get away with this. So there are now cameras that exist, which are called direct detect cameras, which don't use fiber optic coupling, and they allow images to be taken that basically have no effects from camera noise in them, and they only have the effects of what's called shot noise, which is a fancy way of saying the instantaneous variation in beam current coming out of the gun. Okay, we don't have one of these on this microscope. We have the SATA camera is fiber optically coupled, so it's not direct detect, but those cameras actually, they are more effective at working at these really low currents, okay, because they can remove the effect of the instrument noise, which becomes more dominant when you don't have as much signal here, okay? Okay, so that was what I wanted to go over here, is just a little bit of a discussion of beam-induced damage, right? How we see it, okay? And how it can be generated. So, although truthfully, I was actually pretty surprised that it took as long as it did to get that damage before. Again, the area was a little on the thick side, so that's obviously going to be a contributing factor as well. Something that's thinner probably going to hold up a little bit less resiliently. So, all right. So again, we can go back here just to show this. Right. So these are our initial images at spot 4. Okay, very nice pristine lattice here. Okay, and then now this was the first image we took at spot 1, where we upped the current by about a factor of 3. And then we can see what happens with time here, right? We're starting to see the damage here, and now it's becoming more and more obvious. Then we go back to spot 7, okay, and drop our current quite a bit, okay, to only a couple hundred picoamps, and we can see, right, we go back to a pristine area, no damage, but really bad signal to noise. Again, upping the dwell time or the exposure time accordingly, changes our signal here, but makes us a little more susceptible to drift. So, okay. I guess the only other thing we can see, do we want to try and burn a hole in the sample? Why not? Let's see if we can burn a hole in the sample. So I'm going to go back to spot size 1. I'm not going to realign everything though. I'm going to go back to 4 nanoamps, and I'm just going to put the beam at crossover right where we have this gash in the sample, and we're going to see if we can burn a hole. All right, we're starting to see something there. Yeah, let me mess with the aperture. It's gonna bug me. Okay, that's better. Again, I would never do this on the SATA camera, okay? You'll never want to bring the beam to crossover and put it on the SATA camera. That's going to be very damaging to it, most likely. Oh, there we go. I can see. Okay, I can see a hole. All right, let's go a little longer here. Just, all right, so we can see what happens in the extreme, right? In the extreme, we not only introduce, point defects, which agglomerate into extended defects, but we can actually burn straight through the sample, okay? All right, I like it. Okay, let me go back now to spot 4, and we'll take some images of this, some high-res images, so we can really get an appreciation for what's going on here. Okay, it's decent. All right, so let's go back. Now at this point, we might actually have enough damage here that we might be able to see the effect in the FFT, which we really haven't been able to do, at least not very dramatically up to this point. So let's see if we can do that here. And we still really can't. We still really can't see that, but I mean, we can see very clearly there's a hole starting there. So I'm just using the scroll wheel to digitally zoom here. Let me put this back to 1 second, because otherwise 10 seconds will be too much. Okay, there we go. Okay. So I guess the question is, can we see now? One thing you can also sometimes see the effect of this. You can see it in the FFT. Okay, so as you get more disorder in the lattice, what you're going to see is the spots tend to broaden out, which could be, that could be a video topic discussion in and of itself, like, disorder and FFT diffraction patterns. But I'm wondering if we can go do this. We can look at the FFTs before and compare them here so we can see. Let me put, okay, but decent image, right? Let me put the screen in. And while we're doing this, I know we're at spot 4, but I'm going to go ahead and I'm going to keep cooking away here. See if we can't cook a little harder. All right, while we're doing this, let me take the FFT. I'll take a big FFT. So if you click on this, you can do FFT. That's the whole picture. You can also, it defaults to data bar. You can also do it from just a region, okay? So this might be more helpful here. So if we put it, so this is, yeah, so you can see, okay, right here. Actually, let me get rid of the whole area FFT. So this is in the vicinity of the hole. Right, let me do, now I can do another one here, okay? And this is out here away from the hole. And you can see the difference in the spots, right? Hopefully that's pretty obvious, okay? Right, in the vicinity of the spots, you see they get diffuse and kind of blurred out, and here they're much tighter. You do see in all of these, though, in the FFTs, you see these streaks that go left to right. These are a consequence of the FFT processing because we have a square image, so that's why they're in here. You can apply what's called a window over here to try and remove some of that effect. So if we do this here, okay, we can try, yeah, so if you apply the windows, you can remove some of those to make them look more like, a diffraction pattern, okay? Or you can do none, okay? You do lose a little bit of detail though when you do this, when you remove the streaks though. So you can see the spots, they don't quite look as tight even though you remove the streaking. So if we do the same thing here, and we do the same thing here, okay, but yeah, you can see the difference here, okay? Now I wonder also if we go back to one of our first pictures. Not this one. Well, okay. Well, this was at the higher. Let me go to the lower dose. Yeah, this was the last lower dose picture we took. Okay. All right. So you can really see the difference here between these. So let me take another one here. Whoops. Data bar. Data bar. Okay. All right. Now if we go back down to this guy, right? So you can see it looks, fairly similar to what we were seeing here, but definitely nothing like this. Okay. So the disorder, it can be seen in multiple ways, right? You can see how tight the spots are here. Again, if we apply the windowing to them, yeah. So I mean, it looks pretty dramatic here. I'd say this is even better. This was better than what we were getting. Yeah, so I think even here you can see, even away from the main part of the damage, right? We're still seeing a little bit of the blurring of the spots there. If we come back here, all right, we got some beam drift going on. Oh, and we got a nice hole going. All right, perfect. Let me go back here. Ah, there we go. Okay, so now you can really see. Unfortunately, still not really enough detail here in the FFT to kind of help us focus. Or I should say not enough amorphization, right? But we can still see clearly, right, that we've cooked the sample pretty good here. Okay, let me go ahead and take an image as well. Okay, and there it is. So do FFT from selection. Yeah, and there we go. Okay, now you can see what happens to the spots as I move around here. Okay, so over here you can see same thing. They get spread out. So I believe the technical term for this, they call this displacive modulations because we've displaced the atoms from their equilibrium positions. So okay, so I think that about covers what I wanted to go over here as far as the PSA on beam damage. You can see here, right, because of the contrast, right, it got dark everywhere. If I move off of the hole, yeah, see there, it kind of evens out. So yes, we succeeded. I believe we did anyway, of burning straight through the sample. Okay. So, and if you look around too, you can see just in the in the vicinity here, there's the effect of that irradiation, not just in the ground zero, so to speak. Okay, so that's the quick hitter I wanted to do about beam damage. So if you have any questions or comments, please feel free to let me know. Again, I'm a little hamstrung with what I can do, seeing as my Themis is going to be down for a little while here until the gun issue is resolved. But look forward to hearing from you guys. Hope your microscopy work is going well in 2024, and hope you have a good rest of your day. All right, take care.